You know, I was looking at a map of Scandinavia this morning, like really looking at it, and it just struck me how the whole peninsula, it sort of looks like it's trying to pull away from the rest of Europe.
It does, doesn't it?
Yeah, it's like it's clawing its way north, and it's left this gap of cold gray water between Sweden and Denmark.
And that gap, that's the Aresund Strait. It has defined the history of that entire region for, well, for millennia. For centuries, people called it the saltwater curtain.
A curtain. I like that. So it was a wall, basically.
Total wall. If you wanted to get across, you got on a boat, you waited, you hoped the weather held. It was a barrier.
But today, that curtain is, well, it's gone. We've stitched it shut. And that's what we're diving into today, the Aresund Bridge. But honestly, after going through all the research you sent over, just calling it a bridge feels, I don't know, it feels like a massive understatement.
Oh, it's a huge
It's
understatement.
like calling a space shuttle a glider or something.
Yeah. Exactly.
Yep.
The Aresund link is what we in the engineering world call a composite structure, a hybrid. It isn't one thing. It's a cable-stayed bridge that's literally fused to an artificial island.
An island that didn't even exist 30 years ago.
Didn't exist.
Uh,
And that island then becomes the entrance to a massive immersed tube tunnel. So you're right, it's a bridge, an island, and a tunnel all rolled into one seamless, incredibly complex piece of infrastructure.
and that's what really hooked me. It's a whole Nordic noir vibe of it. You see these pictures, and it's this streak of black steel just cutting through the gray mist, and then it just vanishes. It disappears right into the ocean.
It really does look like that.
It looks like a movie set, which I know, we'll get to that.
It has the drama, for sure.
Mm.
But our mission for this deep dive is to get behind that drama and really look at the puzzle itself. Because this wasn't just about pouring concrete. This was about solving a geography problem that seemed, well, impossible. You had airplanes, you had giant ships, unexploded bombs, and two different countries with two completely different electrical grids. It was a logistical nightmare.
And biology, that was the part that blew me away. We always think of these giant projects as, being bad for nature, but this one, it's sort of the opposite, isn't it?
It's an accidental nature reserve. It's a fascinating story. We'll definitely get into how a pile of mud from the bottom of the sea became a sanctuary for rare spiders.
Oh, I can't wait for that.
But first, we really have to understand the geography, because without that context, none of the engineering choices make any sense.
Okay, let's set the scene for everyone. We're connecting Copenhagen in Denmark, specifically an island called Amager to Malmö in Sweden.
Right.
And the distance is about 16 kilometers, so what, 10 miles?
10 miles of very, very difficult water. This isn't some calm little channel. This is the mouth of the Baltic Sea. It's one of the busiest shipping lanes on the planet.
How busy are we talking?
We're talking something like 40,000 ships pass through that strait every single year.
Wow, so lots of traffic.
Heavy traffic, oil tankers, massive container ships, cruise liners, and then in the winter, you have ice flows to deal with. So if you're an engineer in the early 90s, you sit down, you look at this, and your first thought is obvious. We need a high bridge.
Right, you have to get over the ships.
You need to clear the masts. You need to be way, way up in the air.
So you just build a standard suspension bridge, something like the Golden Gate. Huge towers, lots of clearance, ships sail right under, problem solved.
That would be the logical first step, yes.
Hmm.
But there's a huge complication on the Danish side, a very big one. What's sitting right there on the coast of Amager.
Ah, that would be Kastrup, Copenhagen Airport.
Exactly. And it's not just near the coast. The approach vectors, the glide slopes for the main runways, they go directly over the strait.
Okay, I see the problem now.
If you build a suspension bridge high enough for a supertanker to pass under, the towers, the pylons holding it all up, they'd have to be 200, maybe even 300 meters tall.
You're building a giant steel wall.
You're building a steel wall directly in the landing path of a jumbo jet.
Yeah, that's a terrifying thought. So you can't go high because of the plane.
You can't go high. So, okay, plan B, go low. Let's just build a tunnel the whole way across.
I mean, we've done it before, right? The tunnel connects the UK and France. Why not just dig a big hole here?
Two reasons: geology and money. The tunnel was bored through chalk, which is, relatively speaking, easy to dig through. The seabed in the Aresund is limestone. It's much harder, it's fractured.
More difficult.
But the real killer was the cost. A 16-kilometer tunnel that has to handle 4 lanes of motorway traffic and 2 heavy freight rail lines. The price tag would have been astronomical. It probably would have tripled the entire budget.
So you're stuck, can't go over because you'll hit a plane, can't go under because you'll go broke.
And that's why the final solution is so brilliant. It wasn't about some brand new technology. It was about a really clever compromise. They decided to do both. On the Swedish side, which is far away from the airport, they went high. They built this huge cable-stayed bridge that runs for about 8 kilometers. That gets you over the shipping lane.
Okay, so high up in Sweden.
But as that bridge gets closer to Denmark, closer to the flight paths, it has to get out of the way. It basically has a duck. So right in the middle of the ocean, they built an island from scratch. Pebberholm.
The transition point.
The transition point. All the traffic comes off the bridge, lands on this artificial island, drives for a few kilometers, and then dives down into a tunnel for the last stretch to Denmark, passing safely underneath the flight paths.
It's such an elegant idea. It's like a skipped stone that just decides to sink on its last hop. Let's break down the bridge part first, because the notes say it's a cable-stayed bridge. What's the difference between that and a suspension bridge like the Golden Gate?
Well, visually they can look a bit similar, but the physics are totally different. On a suspension bridge, you have 2 giant towers with a huge main cable that drakes between them in a big U shape. Everything hangs from that main cable.
Got it.
On a cable-stayed bridge like the resund, there's no main draping cable. Instead, the cable's running straight lines directly from the top of the tower down to the road deck. It looks more like the strings on a harp, or maybe a fan.
So why pick that design here? Is it just about the look?
No, not at all. It's about rigidity. And this is so important for the resund. This isn't just a road for cars. It's a combined road and rail bridge. And we're not talking about little commuter trains. We're talking about massive, heavy freight trains that weigh thousands of tons.
And I'm guessing trains don't like it when the bridge they're on is moving around.
Trains hate flexibility. A suspension bridge is actually designed to be quite flexible. The Golden Gate can swing meters side to side in high winds. If you put a heavy freight train on a bridge that's moving like that, you could distort the tracks. You could even have a derailment. The cable-stayed design is just much stiffer.
And the double-decker design plays into that stiffness, right?
Absolutely. That's the secret sauce. The bridge deck isn't a flat slab. It's a huge steel truss girder. Picture a long, hollow, rectangular box made of crisscrossing steel beams, like a cage.
Okay.
The cars drive on top of the box, on the roof, 4 lanes of motorway. The trains run inside the box on the lower deck.
Why stack them like that? Why not just build a really wide bridge with the tracks next to the road?
Well, 2 main reasons. First is aerodynamics. A really wide, flat bridge is like a giant wing. It catches a lot of wind. By stacking them, you keep the profile narrow and stable.
Makes sense.
And second, that box shape, the truss, is incredibly resistant to twisting. So imagine you have a hurricane-force wind blowing from the north and a 2,000-ton freight train running on the south track. That box shape stops the whole thing from twisting. It stays rock solid.
Let's talk about how it looks, the aesthetics. The architect, Jorg Rotnos, he wasn't going for a pretty bridge, was he?
No, not in the traditional sense. There's a quote from him where he said he wanted a brutalist expression of strength. He didn't want it to look delicate or elegant. He wanted it to look powerful.
And he painted it all black.
All black, which is unusual. Most big bridges are gray or that international orange or white.
That's why black.
Black creates a silhouette in that very specific Nordic light, which is often low and gray and misty. That sharp black line cuts a really commanding figure against the sky and the water. It looks industrial. It looks like a machine built to do a job.
There's one detail about the design that I just found fascinating. If you look at it from above, it's not a straight line. It has this long, very gentle C curve to it.
Yes, it does.
My first thought was, did they mess up? Or is there something on the seabed they had to avoid? But you're saying it was totally deliberate.
100% deliberate. But it's not for structural reasons. It's for the soft, squishy thing sitting behind the steering wheel. Exactly. If you build a perfectly straight, 8-kilometer-long road over the water with a flat horizon and nothing to look at, you induce something called highway hypnosis.
You just zone out.
Completely. Your brain disengages because the visual input never changes. People literally fall asleep with their eyes open. It's incredibly dangerous.
So the curve is basically a safety feature. It's an alarm clock.
It's a multi-billion-dollar alarm clock. The curve forces you to constantly make tiny adjustments to the steering wheel. You have to visually track the road as it bends. It keeps your brain just engaged enough to stay awake and alert.
That is just brilliant. Okay, so we cross the bridge, we stay awake, and we land on Pebberholm. Let's talk about the tunnel now, the Draven tunnel. This is where it gets really heavy.
This is where it gets really heavy, yeah.
So you said they couldn't bore this tunnel. How do you build a 4-kilometer tunnel under the sea without a giant drill?
Use a method called immersed tube. You basically prefabricate the tunnel on land in giant pieces.
Right.
They set up this huge factory in Copenhagen and cast these enormous concrete segments.
How big are we talking?
I mean, each segment was 176 meters long, about 40 meters wide,
Yeah.
and weighed 55,000 tons.
55,000 tons.
Well,
I'm trying to even picture that. That's like an aircraft carrier made of solid concrete.
it's a good comparison. And they made 20 of them. Then they sealed up the ends, pushed them into the water where they would float, just barely, and used tugboats to tow them out to sea.
Okay.
Then they'd position them over a trench that they had already dredged in the seabed, and very, very carefully they'd lower them into place.
I can't even imagine the stress of that. You're lowering this 55,000-ton block into a muddy trench at the bottom of the ocean. How do you connect them? How do you make sure it's waterproof?
This is the best part. It all comes down to a piece of tech called a GandM gasket.
A Gina gasket.
It's this huge rubber seal that runs around the entire face of the tunnel segment. So when they lower a new segment down, they use these hydraulic arms to pull it close to the segment that's already on the seafloor. The rubber GandM gasket touches the concrete face of the old segment.
Okay, so rubber is touching concrete, but that's not a seal.
Not yet, but here's the magic. They then pump all the water out of the small space between the two seals.
Yeah.
When they do that, the water pressure inside that gap drops to basically zero.
Right.
But the water pressure outside, the weight of the entire ocean, is enormous. That hydrostatic pressure literally crushes the new segment against the old one with thousands of tons of force.
Wait, so the ocean itself creates the seal?
The ocean does the work. That immense force compresses the rubber gasket so tightly that it becomes completely watertight. Then they can just open the doors between the segments and you've got a continuous tunnel.
That is just so clever. You're using the problem, the weight of the water, as the solution.
Beautiful engineering.
Yeah.
But getting to that point was, well, it was chaotic. The timeline was so aggressive. They started in 1995 and they wanted to be done by 1999. 4 years to connect two countries.
That seems impossibly fast for a project of this scale.
It was. And they really only managed it because of one specific piece of equipment. We have to talk about Svanen. Don't let the name fool you. Svanen is an absolute monster. It's a heavy-lift catamaran crane barge. It can lift 8,700 tons in one go.
What does that even look like?
Imagine two ships that have been welded together with this giant steel arch that towers 100 meters into the air. It seriously looks like a villain's lair from a James Bond movie. It was built for another Danish bridge, but they brought it in for the resund.
And its strength actually changed the design of the bridge itself, didn't it?
It did. The original plan was for the bridge, spans the distance between the support pillars, to be shorter, maybe 100 meters or so. But because Svanen could lift such incredibly heavy loads, the engineers realized they could build bigger sections of the bridge on land and lift them into place in one piece. So they stretched the spans out to 141 meters.
And why does that matter, other than just being impressive?
It's actually crucial for the environment. This goes back to the biology. The Øresund Strait is basically the breathing tube for the entire Baltic Sea. The Baltic has low salt, brackish water. The North Sea is very salty. You need that flow of fresh oxygen and salt water through the strait to keep the Baltic ecosystem alive.
And every pillar you put in the water blocks that flow.
Exactly. Each concrete pier creates drag, it creates turbulence, it slows the water down. If you put too many pillars in the way, you could literally start to suffocate the Baltic Sea. By using Svanen to lift these longer spans, they could use fewer pillars.
So the giant crane actually helped save the ecosystem.
It allowed them to meet a really strict environmental requirement called the zero blocking solution. They had to prove mathematically that the finished bridge would not reduce the total water flow by even 1%.
Wow.
And they did it. But even Svanen couldn't solve every problem. I mean, we have to talk about the bombs.
Bombs, right.
You have to remember, this strait has been a strategic military choke point for centuries. And during World War II, it was. Well, it is a dumping ground.
For Allied mines.
Allied mines, German depth charges, old torpedoes. Before they could even start digging the trench for the tunnel, they had to do a massive scan of the seabed. They found 16 unexploded bombs from World War II.
16!
Can you imagine being the diver sent down to check? You're in the dark, cold water, currents are pulling at you, and you find some rusted metal thing in the mud. Is it an old engine block? Or is it 500 pounds of unstable high explosive that's been sitting there for 50 years?
And you can't just dredge around it. If you drop a 55,000-ton tunnel segment on top of a mine,
The shockwave would be catastrophic. It would crack the segments you've already laid. So they had to bring in the Navy's disposal teams to either move them or detonate them in place. It caused a lot of delays.
and on top of that, there was this skewed segment.
Oh, yes.
Yeah.
Segment 13, I think it was. They were lowering it down, and something went wrong. Maybe a current, maybe a winch. It landed on the seabed, just slightly crooked.
How crooked are we talking?
Not much by normal standards. A few centimeters. But for that Gina gasket to work, the alignment has to be perfect. If it's crooked, the water pressure won't compress it evenly. You'll get a leak.
So what do? You can't just nudge
You
it?
can't nudge it. They had to stop everything. They had to pump water back out of the ballast tanks, float this massive concrete block back up off the seabed, realign the whole rig, and try again. It took days. And all that time, you're blocking one of the busiest shipping lanes in the world. The pressure on that team must have been immense.
But they got it done.
They did. In fact, even with the bombs and the skewed segment, they finished the whole project 3 months ahead of schedule.
That's unbelievable. And under budget too, right?
And under budget, yeah, depending on how you calculate it.
Okay, let's go back to the middle. The island. Pepperholm. This island did not exist before 1995.
Not at all. It's completely artificial.
I love the name. The natural island nearby is called Saltholm, which means salt islet. So, of course, the Danes named the new one Pepperholm Pepper Islet.
It's a very dry, very Danish bit of humor. Passes salt and pepper.
So how do you build an island from scratch?
You start by building a wall. They brought in huge rocks from quarries in Sweden and built a big ring, a breakwater. Then all that limestone and clay they dredged up to make the tunnel trench, they just dumped it inside the ring.
Reduce, reuse, recycle on a massive scale.
Exactly. The waste product from the tunnel became the foundation for the bridge.
Now, normally when we build an island, we put stuff on it. Condos, a park, a casino. But Pepperholm is different.
Very different. The two governments and the project's biologists made a deal. They decided to treat Pepperholm as a true tabula rasa, a blank slate.
What do you mean?
They said, we will not plant a single seed. We will not introduce any animals. We're just going to build it and then leave it completely alone and just see what happens.
A giant biological experiment.
A massive petri dish in the middle of the ocean. And what happened was amazing. Life didn't just show up, it exploded. Seeds blew in on the wind. Birds landed and brought seeds in their droppings.
What kind of life are we talking about?
Rare life. You see, Pepperholm is a really harsh environment. It's dry, it's sandy, it's salty, it's baked by the sun. It perfectly mimics a type of coastal habitat that has been almost entirely destroyed on the mainland by farming and development. So species that were struggling on the mainland found this perfect, untouched paradise.
Can you give me an example?
The green toad. It's an endangered species in Denmark. It absolutely loves Pepperholm. It breeds in the drainage ditches right next to the motorway.
That is just fantastic. A highway drainage ditch is a toad sanctuary.
And they found rare spiders, rare beetles, massive colonies of nesting seabirds.
And people are banned from going there.
Strictly banned. Unless you're a maintenance worker or a biologist with a permit, you cannot set foot on Pepperholm. If your car breaks down on that stretch of the motorway, the instructions are to stay in your vehicle until help arrives. You are not allowed to go for a walk.
It's just for the toads and spiders.
And it's not just on the island. The underwater biology changed too. A lot of environmental groups were worried the bridge pillars would be a dead zone.
But it became an artificial reef.
A huge one. The concrete pillars and the rocks around the island it created hard surfaces, which are very rare on the muddy seabed of the resund. They were immediately colonized by millions and millions of blue mussels.
Wow.
And mussels are filter feeders, so they actually help clean the water. And where you have that many mussels, you get predators. Cod, seals, all sorts of fish started gathering around the bridge. So the structure actually increased the local biodiversity.
It's the ultimate irony. We build this massive concrete scar across the sea, and nature just looks at it and goes, oh, look, free real estate.
It just shows you how resilient nature can be if we give it even half a chance.
So it was an engineering success, a biological success.
Yeah.
But a bridge is useless if nobody uses it.
Let's talk about the money.
This thing cost about 30 billion Danish krone, which is, what, around 4 billion euros? Who paid for that?
Well, this is the part that usually surprises people. The taxpayers of Denmark and Sweden didn't actually pay for the construction.
What? How is that possible?
It's entirely user-financed. The two governments formed a company, and that company took out huge loans on the international market to build it. But the deal was, Those loans have to be paid back entirely by the tolls from people using the bridge.
So every time I drive across, I'm basically paying the mortgage.
You are paying the mortgage, and it's a very big mortgage. It costs about 60 euros, so roughly 65 US dollars, for a single car trip.
Ouch. That is a pricey commute.
It is. And when the bridge first opened in 2000, that was a huge problem. Traffic was way, way below what they had forecast. People looked at that price tag and said, no thanks, I'll just take the ferry.
The dreaded white elephant project.
It looked like it for a few years, yes. But then simple economics took over. Around 2005, housing prices in Copenhagen just went through the roof. But in Malmö, just a 20-minute train ride away, it was still much more affordable.
Ah, geo-arbitrage.
Exactly. Danish families realized they could sell their tiny apartment in Copenhagen, buy a big house with a garden in Sweden, and commute across the bridge every day. Even with a toll or a cheaper monthly pass, the math just worked.
Oh, the bridge effectively merged the two cities into one.
Economists call it agglomeration. You took two separate, medium-sized labor markets and you fused them into one giant one. A 2022 study I saw said the bridge led to a 13.5% increase in average wages across the region just by creating this bigger pool of jobs and talent.
Which brings us to the trains, because the cars are one thing, but the train is the real workhorse here, right? 15 million passengers a year.
The train is absolutely vital, but getting a train to run smoothly between Sweden and Denmark is a technical nightmare that most people just don't even think about.
Why? It's just a track.
You'd think so. But of course, Sweden and Denmark use completely different electrical systems for their railways.
Of course they do.
Denmark uses 25,000 volts at 50 hertz, which is pretty standard for Europe. Sweden uses 15,000 volts, but it's 16.7 hertz.
That's not just a different plug. That's like a whole different kind of electricity.
It is. And the signaling systems, the things that stop trains from crashing, they speak completely different languages.
So do the trains have to stop and change engines at the border?
No, that would kill the whole point of a fast commute. The trains they use are special dual voltage models, but the switch itself, the switch is the really cool part, and it happens on Peberholm.
The Magic Island strikes again?
On Peberholm, there's a short, neutral section of track where there's no power in the overhead wires. It's a dead zone. As the train hits this section at full speed, the computer senses the power cut.
And it just coasts through.
It coasts. And while it's coasting, it lowers the pantograph, that's the arm on the roof that touches the wire. While the arm is down, the onboard transformer reconfigures itself from the Swedish system to the Danish system. Then the arm goes back up, hits the new wire, and the power comes back on.
And this all happens in just a few seconds.
A few seconds, at over 100 kilometers an hour. And at the same time, the driver has to manually switch the signaling system on their dashboard from Swedish to Danish. It's this incredibly complex digital and mechanical ballet that happens on every single crossing.
And the passengers are just sitting there on their phones with no idea it's even happening.
That's the goal. But if you listen really closely, some people say you can hear the hum of the train's electronics change pitch right as it crosses.
That's a great detail. But while the technical connection is seamless, the political one hasn't always been. We have to talk about the border.
Right. The whole dream of the bridge was a borderless region. You had the Nordic Passport Union for 60 years. You could travel freely. The bridge was the ultimate symbol of that.
But then 2015 happened.
The migrant crisis. Sweden got nervous and reintroduced ID checks at the border. All of a sudden, every train had to stop. Everyone had to get off, line up, show their passport to the police, and then get back on the train.
That completely destroys the 35-minute commute.
It added 30, 40 minutes to the journey. It broke the flow. It was a stark reminder that even though the concrete is permanent, the political openness can be fragile. The psychological distance between the two cities grew again overnight.
It just shows that a bridge is only a bridge if the law actually lets you cross it.
Precisely.
Okay, we can't wrap this up without talking about the culture, because for millions of people around the world, myself included, the first time we ever saw this bridge wasn't in an engineering magazine. It was on Netflix.
The Bridge, or Bron and Bron.
The show that basically launched the entire Nordic noir genre.
It's an iconic show. And the premise is just perfect for this discussion. A body is found lying right on the borderline in the dead center of the bridge. The top half is in Sweden, the bottom half is in Denmark.
Which forces the two police forces and their very different personalities to work together.
It turned the bridge into a main character. Before that show, it was just a piece of infrastructure. After the show, it became this moody, gray, mysterious, and slightly dangerous place that brutalist black steel that the architect wanted. It was made for the camera.
It gave the whole region a new identity.
It really did. People used to talk about Copenhagen and Malmö. After the show and the bridge, people started talking about the resund region. It put them on the cultural map as a single, cohesive place.
So what's next for the bridge? It's getting busy, the trains are full. Is one link enough?
It's probably not going to be enough for long. There's another huge tunnel opening soon that connects Denmark to Germany. That's going to send a massive new wave of freight traffic north. And the Øresund Bridge is going to become a major bottleneck.
So are we talking Øresund 2.0?
There are a few proposals floating around. A new tunnel further north called the HH Tunnel, or my personal favorite, the Øresund Metro. A dedicated, driverless subway tunnel running directly between the city centers of Copenhagen and Malmö. It could run every 90 seconds. It would take all the daily commuters off the main bridge, leaving it free for freight and long-distance travel.
A subway under the Baltic Sea? I love it. It feels like once you prove a connection like this is possible, the appetite for more just keeps growing.
That's the main lesson here, I think. Geography is no longer destiny. We can literally change the map.
So to sum this all up, we have a bridge that was designed to duck under airplanes, a giant crane that accidentally saved an ecosystem, an artificial island that became a sanctuary for endangered toads,
And a train that performs electrical surgery on itself while it's moving.
and a very expensive alarm clock if you count the curve. So for everyone listening, here's the takeaway. If you ever find yourself in that part of the world, don't fly between those two cities. Take the train.
Definitely take the train.
But when you're crossing that water, don't just look at your phone, look out the window, look for that black steel, look for the curve.
And as you pass that little green island, just remember, you are riding on a piece of the seabed that was dragged to the surface where a bunch of rare spiders are probably watching you zoom by.
And maybe keep an eye out for a detective driving a vintage Porsche. Thanks so much for diving in with us.
My pleasure. See you next time.